I think it might be independent qubits. Like if you so it's more like an expected communication code. So if you run this product, if you want to send n independent qubits, you're going to you're going to get. I think on average you're going to need about n classical bits to do this.
Yeah, thanks. That completely answers the question, because that's also how much you need to encrypt.
Okay, but this is like to consider protocols in the literature, and now we are going to introduce our protocol. Okay, so which we call port-based state preparation, which is a combination of port-based teleportation and remote state preparation. So in this scenario, we still don't allow Bob to do any correction operation. Yeah, we don't allow Bob to do any correction operation, and we also give the complete knowledge of the state to Alice. So we are in these two scenarios. Before, in port-based teleportation, remember that we didn't allow corrections, and in remote state preparation, we gave complete classical description. What if we combine these two restrictions? What happens with the relation between the number of ports and the classical communication cost of the protocol? First question is, can we build such a thing? And if we build such a thing, what's the relation between these resources, right? So we can build such a thing very simply. We will, for simplicity, just assume that the shared resources are independent, maximally entangled states. Very simple scenario. And we can, so if we have that the resources are independent, maximally entangled state, then the protocol is uniquely described by the measurement that Alice makes. Right? Because Bob can only communicate the port, so the cost of communication will be exactly the number of ports I have. And now the measurement will be enough to describe the trade-off. So we can distinguish two types of mesh protocols. We can describe probabilistic protocols where we have n+1 elements in the POVM. The first n elements will just tell Bob open port I, and the n+1 will be aboard the protocol. So either after the measurement, the state is in one of the ports or it's nowhere. And if it's nowhere, Alice just will tell it's nowhere, and they will have it hasn't succeeded in the protocol. And what the figure of merit in this case will be what's the probability of succeeding. So what's the probability of not having outcome n+1, the outcome of not finding the qubit. And we can also describe the deterministic variant where we have Alice always gives an answer to Bob. So there's n elements in the POVM, but then after the answer, it might be that the qubit is not fully in one of the ports. So we study the fidelity of the outcome port with the desired state. So a very simple measurement that we can do is we just check if the state is in any of the ports. Because we have many copies, as Ronald pointed out before, you can just check independently, is it here, is it there, with a projective measurement. And there is also this property of EPR pairs, is that if I project to the conjugate of the state, then I will get the state, and I trace out Alice's view, then I get the state with probability 1/d.
It was actually measuring the state, not detecting the qubits. It's actual measurement.
Yeah, detecting the qubit.
As if these were photons, if it's just like a detector of the number of photons. I was just wondering because that would be very non-trivial.
No, I don't know.
Yeah, okay.
But it's measuring.
Okay, thank you.
So for the probabilistic port-based data preparation, we describe the following measurement. Like it's a bit complex, but what's just saying is the measurement outcome is X, like port number X. It's just like a normalization of, because it could be that the qubit is in like 2 of the ports or something, and then you have to spread the probability somehow, that this doesn't matter so much. And then the probability of like failing, so not finding a qubit in any of the ports, is just projecting to it's in none of the n boxes. And this will be like the probability of failing here, like X is 0. And what we...
The state size, the one that you want to.
Yeah, so the state size is the one that you want to send. So you prepare like the predictive measurement with the conjugate, and because of this property, if you find the conjugate, then on both sides there will be the states you want to do some problem.
So this is a POVM. What could it look like in practice? How do you build it?
How are POVMs built in practice?
Yeah, okay, you need more copies, larger helper spaces, and so on and so on. To build it. Lots of ancillas.
So in this case, I mean, you first need a projector onto psi conjugate, but I guess you could, so that depends on like the circuit complexity of psi. But let's say you just have that as a box. That I think like you just input a state and then you project into it or not.
Okay, so you wouldn't need any ancillas to implement a POVM.
Then you only need a few ancillas, and they can basically be classical processing, right? You can
Okay.
you're basically just
Yeah,
measuring
yeah.
everything independently.
It looks like simple projections, yeah.
Project as a simple projection, and then you just randomize if you have multiple successful outcomes. But I'm not sure, like the circuit, I don't know. But it's not horrible.
Okay, so the probability of success of such a protocol is like 1 minus the probability of failing. And the probability of failing is like the state will not be in each one of the ports with probability 1 minus 1D. Because we said with 1D, it will be there. And then you have n ports. So this like, it's in the exponent. So like a bit, what's interesting here is that if you only have one copy of the state, then you cannot do this independently. So the measurement, like, I don't know, like if you have many copies, then it's like if you were doing independent coin tossing, so you can have this like exploding factor, like the exponent, which is not the case for port-based teleportation.
Is this the same as just doing teleportation many times and then post-selecting on it being in the 0 state one time?
But
Like it
teleportation-
being like is this a different protocol than just doing like teleportation with my first EBIT pair, then oh, I didn't hit the version where it's like without any error. Okay, I go to the next one. Let's
Yeah.
try it. Is that the same as this?
Yeah, basically because you are projecting, is it here or not?
Almost one quarter, but your 1/4 of the ports would be teleporting in the correct way.
It's quadratically better. It's like,
This is quadratically better.
because it's like doing state preparation in time instead of doing what teleportation. Right? If you would do that, you would get 1/d squared instead of 1/d.
Ah, okay.
Is this the dimension of the state you want to teleport?
Okay, and then the deterministic variant of this is just as it, so we now don't have the probability of failing, but we will just spread this probability of failing among all the ports. So you just like take the previous measurement and you just spread this probability of failing evenly among all the ports. And you have like the measurement, a measurement that gives you like some fidelity. That's exactly the same fidelity as the probability of success of the probabilistic port-based preparation. So like these two things are different in general for teleportation, but because of like how we constructed this measurement, basically when you calculate the fidelity, all this doesn't contribute anything because you are like the orthogonal of the state that you want to project. So that's why they are the same. In principle, the fidelity is always greater than the probability of success because you can spread this in different ways among the measurement. So it will be at least the probability of success plus some probability spread.
And the fact that you know the states, that is kind of reflected in that the M0 and all these M's depend on.
Yeah,
Right.
yeah, exactly. The measurement that Alice does depends on the, and like in each port you are able to do a projection to that.
If you don't, in the case in which there is no port-based, what is the optimal measurement? You said that in the first case is a pretty good measurement. In the second variant, what is?
In the remote state preparation variant.
Yeah.
I don't know. I don't know. Okay, so this is like an existence result. But now we are going to look like how good can we make this? How good can we make this port-based state preparation protocol? So we looked at this in the case where the shared resources are in EPR pairs. And the argument is very simple because it's just using non-signaling. Let's see if I can explain it. So like we have this, like some resources, and Alice knows the state she intends to send. But now for the sake of argument, let's just assume that Bob also knows the state that Alice intends to send. Yeah, so what Bob can do if he knows the state is, well, he can just measure, like, is the state in any of the ports? And like measuring is it nowhere? And then the opposite of that, is it like in some of the ports? That's the question he asked. And the result is that it will be in some of the ports with certain probability of success at like the time before Alice has done anything. And now imagine that like afterwards, Alice makes some measurement. And if there exists a port-based state preparation protocol with probability of success P star, then with probability P star, after Alice makes the measurement, there will exist a port that contains the state, because that's just like the correctness of port-based state preparation. So if there exists a state that if there exists a port that contains the state, then if Bob makes the measurement after, like now imagine if instead of in time 1, Bob makes the measurement in time 2, then the probability of Bob finding the state in some of the port will be bigger than P star, because like by correctness, Alice has found it in some of the ports. And yeah, and because like she has found it, but there has been no communication like in this time. So then the probabilities of success cannot be different. They have to be the same, which basically gives a very stupid, simple upper bound for the probability, lower bound, upper bound for the optimal achievable probability in such a protocol, which is the bound that we gave for the EPR resources. But it only works for EPR resources, like this way. Like in summary, like we've introduced this port-based state preparation, we've given a protocol that achieves certain fidelity and probability of success, which is the same. And then we've shown that this is achieved, it's the optimal if we have EPR resources. So the measurement that we give achieves the optimal if the resources are EPR pairs. You can compare it with like known protocols for port-based teleportation. Maybe they are not like all the best ones. This is what I found in the literature. But what you see is that the optimal fidelity scales inverse quadratically in the number of ports. And in our case, there is this number of ports in the exponent. So that's like a very different behavior. But this is what I told you, that you are able to do coin tossing here, but not here. We also see that for the port-based teleportation protocol, the fidelity and the probability are different. And in our case, they are the same. But even the optimal achievable ones are different. And for us, they look the same for EPR pairs. But here, they optimize both the measurement and the resources. So it will be interesting to see. It will be interesting to see also what happens when we optimize the resources. Like, do we get some difference? I don't know. What do these like optimized resources look like? Who knows? And also the measurement. Like we give like the measurement that seems natural, but maybe it's other measurements. I don't know. Okay. And now.
Sorry, do you know which are the optimal resources for port-based teleportation?
So for like the deterministic and the probabilistic ones, they are different. I think for both of them, the optimal measurement is a pretty good measurement in some regime, but the resources are not the EPR pair, but I don't know what they are. I just know they are not.
Basically, when you say optimize resources, it's number of APR pairs that you have?
No, it's not number. Like instead of having an EPR pair, what if you share like a general entangled resource? Maybe it's not like the maximally mixed state. Maybe I like you will have to do a SDP for that.
Yes.
Yeah.
So at some point you said, what happens if Alice just measures every qubit independently in the side and side?
Yeah.
Like, why can't you do that? Like, because your measurement is complicated. Like, so, can you remind what happened?
Sorry, why can't you do that well?
Like you said, at some point you said she would just like, look, is it, yeah, like you said, check it to state size and
Yeah, she does that, right?
But it's like, I guess I understood that as she would just measure independently every qubit in the basis like psi versus psi third. And like that's the procedure. And I understood that that's not optimal, but you have.
No, that is what we do, sort of. We just have to like normalize properly. Because it could be in two places.
But could you say that your measurement is just orthogonal measurement followed by some kind of like post-processing that you just post-process the outcome? I guess.
Is it? I mean, if you do independent teleports of the same state n times, n/4 of them are going to be unencrypted. So you get n/4 perfect copies on the other side.
Yeah, that's basically this procedure in a sense, but except you just put it in the measurement instead of describing it as a. I mean, the probability will be the same of success. I think this is kind of the same probability as you would get if you just project everything independently, and then for all the successes you get, you toss a coin and pick a random.
Right. Because like, I think if that's the case, then your protocol actually sort of does better in the sense that, you know, Bob can get not just one copy, but he might be lucky and get several copies. Like, so Alice can sort of, I mean, she could send a whole subset where the measurement succeeded and then. You get more copies.
Yeah. Yeah.
Sorry, can you repeat why are these the optimal value of the probability of success or the optimal value of the maximum fidelity?
So why this? No, what we do in the non-signaling argument. So we know that if you do this measurement, the probability of success is this one. But then we show that imagine there is in the non-signaling argument, it was like imagine there is another general measurement that Alice can do that succeeds with probability P star. Then this P star has to be, if what they share is maximally entangled resources, then that P star has to be like lower than this value. And we already know that you can achieve this value. So then that's the optimum. Yes, do you want? Yeah. Okay.
Here the fidelity is the fidelity on every qubit of Bob? Or there is one qubit with that fidelity.
So like Alice will send one port and it's the fidelity of the qubit in that port with what she intended to send.
Okay.
We haven't checked or like, we don't look at it because of how we devise the protocol, but that's what Mari said, that if you like check them independently. Here it's because we are saying, oh, if the qubit is in two, like the size of the subset where the qubit, where the state is 2, then we like randomly pick one of the ports, but you could also say like, oh, it's in like this port. Okay. Okay, so now let's just give like some application of this port-based state preparation, which is doing universal programmable hybrid processors in analogy to universal programmable quantum processors. So what is this? It's like a big machine to which you give a classical description of a state. And then the machine will compute any unitary on that state but by making some calls to a memory, which will be, the memory will be like an ensemble of quantum states that somehow encodes the unitary that the machine wants to compute. And by making calls to this memory, we'll have like the unitary applied on the quantum state. So we give a classical description of a state and the machine computes a unitary on a quantum state. And like, how can we build this? Like if the input is a quantum state, then there is this no-go result that for each unitary that you want to apply, then the state encoding this unitary somehow has to be orthogonal. So if like, because there's like infinite unitaries in the dimensions, then the dimension of this memory will have to be infinite because you want like an orthogonal state per unitary that you want. So that's why, like, instead of having perfect like processor, we say like we allow some error. Now what we want to study is like the relation between the error of the machine, the dimension of the unitary or the state, and the dimension of the memory.
So the unitary, how is it input into this machine? Is it like this memory state? Is that and so it's a quantum state. It's a quantum state has a description.
So like the memory will have a quantum state that has the description. Okay, so we will build this with the like the port-based state preparation by just saying that this memory will be the EPR pairs that we had in the protocol, like the shared resource to which Bob has applied the unitary. So it's basically like the choice state of the native. So like this is the memory. And now the processor is just doing the protocol for port-based state preparation, like gets as an input the classical description of the state, like does the protocol by making calls to the memory, which is just like this unitary applied on Bob's half. And then like when you pick a port, you get the output, the unitary applied on the state.
So in effect, you try to sneak in the state before the unitary is applied. Is that how I could understand it?
Sneak in the state.
Like kind of like you're projecting on the left, the states that you have on the left, right? But this unitary is somehow applied to a lot of these EPR pairs.
Yeah.
But now, because you do this projection, somehow this EPR pair changes into the state that you wanted to have in there. Or is that not what you think?
I don't exactly understand your question, but it's basically that in this protocol, because Bob doesn't do any correction operation, and that's also answers your question, why is it important that doesn't do any correction? Then Bob in particular could in the beginning apply the unitary on all the states, and then the correction that Alice sends won't alter the state. Like if this was done with like teleportation, then the problem is that if you got like some correction to do, then this correction doesn't necessarily commute with the unitary. So yeah, you want a correction that somehow like that commutes with the unitary in a way. And if you don't have any correction other than looking at it, this I think it's called like this covariance property in the literature. Okay, and like, so what's the trade-off between the memory and the dimension of such a protocol is like the dimension of the memory is this like n ports that you have, and each of the states has dimension d. And if we check the number of ports that you need to achieve certain correctness in our protocol, we can give that the memory dimension of this scales in the error as d log d, basically. So this is like an existence result of a hybrid processor. And now we are also going to be like, what's the maximal achievable like scaling in the error and the dimension, like this trade-off that we can achieve with like a general processor without building it with port-based state preparation.
Sorry, the word hybrid is because the state is classical. Like why do you call it hybrid?
Yeah, the hybrid is because it's like classical input, quantum output. And there exists, I mean, if everything is classical, then it's a computer. If the input and the output is quantum, this exists like called Universal Programmable Quantum Processor, which is also web studied. And hybrid is it because it's something in between. Yeah. It's a very imaginative one. Okay, so for like a impossibility result, we do this by relating the UPHP to quantum random access codes. And we know like for a quantum random access code, it's something like we have n bits and we are trying to compress like classical information into qubits. And then we give like a set of measurements such that for each measurement, you can retrieve at least one original bit with certain probability of success. It's something like that. But okay, like the bad side is that we cannot do this very well. Actually, like for this is called like the NIAX bound is the number of qubits you need is at least like the number of bits that you were trying to encode with some like wiggle room, which is like the entropy of the error that you allow, like this probability of success. So it's not very useful. And we are going to see that if you like universal hybrid processor is doing a random access code, and this cannot be very good. So the hybrid processor also cannot be very good.
The usual definition of random access code is that for each index I between 1 and n, there exists a measurement that can be covered by the data.
Yeah.
What do you mean?
Yeah. Am I not saying that?
Very different.
Because you say that I give them, no, okay, it's what you say, that for each bit there exists a measurement that can retrieve it with some, but it's still not very good. Sorry, okay, yeah. Not very
What
accurate.
you're right is easy to achieve by just sending x1.
Yeah, yeah. Sorry. Yes. Okay, yeah, for each bit there is a measurement that cannot retrieve it with certain probability, but then still. Yeah. So we are going to build this. Okay, so like the Q, like this is just for like in the parameters that we are, but it's like some bits, some qubits were being called, and like a set of measurement that cannot retrieve. Like intuitively, what we do is that these qubits that we encode are basically the memory. And so what we want is if we have some bits, we can see this as like a Boolean function, and like a Boolean function we can see it as like a unitary. Maybe this is a bit hand-wavy, but it's to like get the picture of how quantum random access code relates to processors. So you have like some unitaries with certain dimension related to like number of bits. So we are trying to encode these unitaries in like some qubits such that we cannot retrieve it. And this qubit will be the memory. And the processor will be like some measurements that we do so that you can retrieve like the unitary applied to the state. And like by like the NIAX bound applied to like this memory measurements, we see that the number of qubits has to be bigger than d/2. Like, and this is like number of bits and then some error. Yeah, like, so, you know, we have to construct the measurement, like there is a bit of like how to write, but it's basically that if you have a processor, you are building a quantum random access code, we have like an impossibility or like a difficulty of building quantum random access code. So these processors also cannot be very good. So the dimension of the memory has to increase exponentially on the dimension of the unitary we want to encode. So like, how does the table of comparisons look for hybrid processors? We've built a hybrid processor where the memory scales as d log d on the error. And we've shown that you cannot build something better than a memory that scales. Oh, this is a 2, not a 4. Okay, well, as like 2 to the d with some error. So for the quantum case, where we have quantum input and quantum output, there is like the gap between the existence and the optimality is closed, where the exponent is d squared. So in particular, the hybrid processor is better than doing quantum like processor, but that's a bit what we expected. It's just like there is a gap, like it's strictly weaker, or it needs strictly less memory to compute it. But there is also, we could only show a lower bound on the memory that scales exponentially in the dimension. That is better than the one by Kubicki and Palazuelos for the quantum processor, but it's not exploding in the error. So that we still, like, there is a gap between like the existence and the exploding in the error that, you know, like if this error tends to 0, this doesn't go to infinity, but we would like ideally want to know a result like that. It's just that the tools used for quantum processors don't really work in this setting. But okay, like I guess the question is like, can we give like a tight bound for this and yeah, and that's it.
So that seems to be, I mean, related to the tightness of Nyack's bound. Isn't there something known about it?
Well, no, like the Nyack's bound gives us, because of the Nyack's bound was, I don't know, like just how the Nyack's bound looks is very different. Like if you even, like what else can you achieve in the
Yeah, but I
tightness?
mean, you show that whenever you do this construction, you get a quantum random access code. So if you have better constructions for random quantum random access codes, then they may give you better universal programmable hybrid processors.
But you have an impossibility result for quantum random access code, right?
That's
So
only
you
one
don't
way.
have better.
You can embed a random access code as an example of something a programmable hybrid processor can do. But the hybrid processor can do more things. It's like a discrete subset of operations you might encode as your program. But there's like a continuous set of other stuff you might also encode as programs.
So that will be a way to get better lower bounds. I guess you're hoping for better lower.
But I don't think like the Nyack bound is the way to go because of like how, I mean, another bound for. So like how in the quantum processor case, these bounds work is that they have some independence between, like the input is a quantum state and the memory is also a quantum state, and these two are like separated. So they can bound the overlap of the inputs in terms of the memory, but we don't have anything like that anymore. So it's just a bit different. I mean, okay, and then also like this result is using like Banach space theory. But in particular, our bound, which has a 2 here, is better than their bound. So like that might have been another way of showing a lower bound, but we have a better one with Nyack, which is way similar. So I don't know exactly how this goes. And also it's not clear if it's like, if this goes to D or this, like where the tightness is. Maybe we can. Okay, but that's it.